transmit different rates of information. So on Wi-Fi and other radio technologies, and like there's few megahertz or few gigahertz or 20 gigahertz. But when you get to lasers, it's an entirely different challenge. Like it's a few terahertz of bandwidth. So you have different challenges. So I'll just go through the PAT first, the pointing, acquisition, and tracking. So the main goal over here, if you break it down, pointing, acquisition, tracking, you have to first acquire the other side. You have to point to it, and then as the other guy moves, you have to track it. Because like I said, if you need millidegree kind of precision, every meter, for example, if one device is on a pole and on a top of some like really tall building, and a truck passes by or something, that pole is going to sway a bit. So that swaying is going to translate to the beam wandering like a few meters on the other side, and then you're going to lose the link. So the challenge here is to find out where the other guy is and point to it and keep tracking the other guy to maintain the link. So there's like, in an ideal situation, it's pretty easy to find the other guy, but in real world, you have, firstly, just to acquire the other side, you might have like random mirrors on the other side. Like, for example, if you send something for the other guy to like respond back to, you might get reflections. Or if, for example, you have the other guy sending something, then you might see multiple of, okay, find a better way to say this.
Well, for instance, I mean, it's very easy, and like okay, like if you take for instance like the sun can reflect to something, even just like the building, if it's painted white, it's going to reflect a lot. And for sure, the frequencies of the suns can match whatever is the frequency that you want.
We're using laser, which is kind of, the sun emits a lot of that frequency. So if it's getting reflected off some window, you're going to detect that also as like another device. So just to give you like an example of the kind of view we're looking at, I'm just going to play this. Just going to play this video to show you what the other side looks like. So this is a very simple kind of situation. We just have a window, you have a device on the other side, and then very simple case where you have something on the other side, and that's basically the laser that the other guy is shining at towards you. So both sides are shining lasers towards each other, and that's what they use to see or find each other. So in this kind of scenario, if you look closely, the image is not still. If you see this tiny kind of turbulence in like the overall scene, and it's not uniform. Like the whole scene doesn't move left and right. It's some parts of it move left, right, up, down. And this is just the, like if you look at a really far away building on a hot day, you will see that because of the motion of the hot air and the cold air, it will cause some kind of atmospheric turbulence. So that is my next point. So what we have to do essentially is get around that kind of problem where you don't take this kind of atmospheric turbulence into account, because right now it's slow. If you look at space, this is just like a distance of 100 plus meters. But if you go and look at the same thing in space, ignore the audio. This is a stationary camera looking at a star. So this is what it looks like if you go far enough. And for example, if we did, like in this case, none of the sides are actually moving. But if you respond, if you detect that as motion and then you respond to that motion, you're going to start pointing in like weird directions that you're not going to be able to send the beam to the other side. So that's atmospheric turbulence basically. And then, like I mentioned, you have to point to like a milli-degree kind of precision. So you have, like for example, if you have a camera sensor, you have, that's in terms of the camera sensor, you have to have sub-pixel accuracy. Like you have to find the object and locate it within like 0.1 of a pixel. Yeah. And finally, like once you know where to point and once you know how the other guy is moving, you need to be able to send all this data to your controller, and then be able to send that to a motor that controls where you're pointing. And this needs to take into account your information of how your device's like physical inertia and like how it basically moves around, because you need to know how it, because we tried, like simple PID and stuff doesn't really work in these kind of situations when you need a few kilohertz of correction. Yeah. So this is mostly about pointing and tracking. Okay, one question a lot of people ask us is, if it's a laser comm and it's not radio, it doesn't really penetrate walls. You need a line of sight, like you need a clear view. So a lot of people ask us what happens if there's birds in the way. So this is what happens if there's birds in the way. We've captured a lot of photos with birds like actually blocking our link. So they do block our link and birds are fine, they don't die. This is another example of, it's not enough power here. Another example of what I wanted to tell you, like sometimes there might be like sun and shit reflecting off. So if you see this one, this is where the actual device is. But you see there's this little shit here, which if you detect wrongly which one is the actual device, you'll be pointing the wrong way. So yeah, you need to have techniques to get around
you need to
that.
take into considerations that it could be, let's say, also something like that can be moving and that can reflect lights and that can actually overlap to your pointing to the pointing where you were pointing before.
Yeah.
And while these move away, then potentially you don't want to get taken by that specific point. You want to keep staying to whatever was your original position.
Yeah, like if you see this is a building behind, and those are like glass windows. So at a certain point in the day, the sun will actually reflect off those glass windows, and there'll be like a huge big source of energy that's coming towards the device, and you need to make sure that you don't look at that. While at the same time, you need to also ensure that you track that even when someone is like banging on the floor, that you are on. So yeah, the second point, which is optics, so like I said, milliradian optical precision. But one thing that people forget is it's not just you make it once and that's it. That works in a research lab, and that's something that we've done a lot of times. But to do it repeatably and to do it in a way that it doesn't so we call it like optical calibration of certain devices. So that it doesn't miscalibrate itself over time or over temperature cycling. That's another huge challenge. And this kind of calibration is really important for us because, for example, if you have a camera looking at the other side and you know where you're supposed to point, but actually if your laser over time, I don't know, something expands or contracts and starts pointing the other way, then your source of truth is no longer your source of truth. So the way you point your laser, the way you are accepting your incoming laser beam, and the way you're detecting, these three elements need to be perfectly calibrated, and they need to stay calibrated over long periods of time. So that's a real challenge. And doing this, like you can imagine, if for a short distance you calibrate everything is good. You take it to a distance of like 3 kilometers. The 1 meter calibration that you did needs to work exactly the same in 3 kilometers. So even if you had a small error there, like again, millidegree or less than a millidegree, it's going to translate to a huge error in a longer distance. So we need to make sure that it works. We are able to test this whole system in a small distance, and it works the same in a large distance as well. And one big challenge that it doesn't seem very obvious, but it is, to focus all of the power on one spot. So the image that I've shown you guys here, it's called spherical aberration. And if you take like a spherical normal lens and you like focus parallel light through it, it's not going to focus on one single spot. It's going to focus something like the image below. It's all going to focus on, so it's not going to be one point, it's going to be something like this. So it's, you call it the PSF, the point spread function of a lens. So that's what you get in a standard spherical lens. So one challenge is, how do you, okay, that's why if you guys have seen like a lens of a DSLR, it's not made of just one single lens. It's made of a lot of different lenses. which all compensate for different aberrations, like chromatic aberration, spherical aberration, and stuff. So we need to do the same thing, just that we need to make it such that it points to something that's the size of a fiber core, which is really, really small. And yeah, we need to make sure that it's temperature tolerant and it doesn't move around when you need to go make it, transport it or make it work at different distances. And yeah, finally, the last part is modulation and coding. So if you guys are aware, usually when you transmit